Hi everybody. Today we're going to talk about the strengths of acids and bases. So one of the questions that comes up is what makes a strong acid strong and what about a weak acid? So first of all, you have to understand the strong acids are part of that group that is found on our data booklet. So when we look at our data booklet here, the ones up here in the top that are gray, these are strong acids and they will completely ionize. And we see that because we see this arrow going in one direction. So a strong acid completely ionizes. So here HCl with water turns into, and you see the single arrow going in the single direction into chlorine ion and hydronium ion. A weak acid, on the other hand, only partially ionizes, which means it's at an equilibrium. You can always tell because they'll have an equilibrium arrow. So these here in the white, these are all weak acids. So we have the acids on this side, the bases on this side, the Ka, which we'll talk about in a second. And acids get stronger as they go up here. Now, notice how I say stronger, not strong. These are all still weak. It's just the ones here, like iodic, are stronger weak acids than something like nitrous. Bases are the reverse. They get stronger as they go down towards these guys. So here are your strong bases, and everything on this side, the right-hand side, is a base. Next class will teach you how to calculate Kb versus Ka, but for now, you'll be able to calculate Ka. So when we look at an equilibrium expression, and we've seen a lot of equilibrium expressions for acids and bases, instead of KSQ or KEQ or KSP, we use Ka for the acid equilibrium constant, and that's basically the concentration of the products divided by the reactants. Remember, we don't use liquids like water in there, and so we just have this. And the smaller the Ka is, the weaker the acid, basically, which means it's going to favor the reactants. And vice versa, the stronger and the larger the Ka is, the stronger the acid is, and the more it favors the products, especially the hydronium ion. Okay? Bases act in a similar way. So bases act like you have the same sort of thing, but it's Kb instead of Ka. And once again, we don't put water in, and it's the products divided by the reactants. The larger your Ka, the greater your hydronium ion is, and the larger your Kb, the greater your hydroxide. And only a change in temperature will change the Ka or Kb. And an increase in Ka or Kb will cause a shift towards the right, towards the hydroxide or the hydronium. Now, when you have an acid or a base reaction, or sorry, an acid and a base reaction, when you're mixing the two of them together, one side will be stronger and the other side will be weaker. Okay, so we have if we look here, we have hydrocyanic and a bicarbonate ion, and it's going to form cyanide ion and a bicarbonate acid, or a carbonic acid. So if we go back to our chart and we look down here, we can find that, let's see, hydrocyanic is here and carbonic is here. So carbonic is closer to the top, therefore it's the stronger of the acids. So between HCN and H2CO3, this is the stronger of the acid. And then we look at the bases. The HCN is further down, closer to the base compared to the bicarbonate ion. Therefore, the Cn minus, that is the stronger of the weak bases. And so we write stronger and weaker. Notice we have a stronger side and a weaker side. And the equilibrium will always favor the weaker side. So it's going to, in this case, shift to the left. Thanks. I hope that helped.